Okay, right. So to recap what we did last lesson, we use the concentration time graph to find the half-life. Okay, you can only do this with concentration time graph because half-life is the time taken as the concentration goes down by half. So that's what half-life is. Okay, on this slide, it is showing you 3 successive half-lives. Okay, successive means continuous. So the first half-life is between 0 to 17, okay, ish. The second half-life is between 17 to 34. Okay, and the third one is between 34 to 51, roughly. So half-life is just that portion. You do not start counting the time from 0. Okay, so you only start for the first half-life from 0 to 17. That's when your concentration starts from 4, it goes down to 2. When your concentration starts from 2 and went down to 1, the half-life is that portion. Okay, and then we looked at how we can use the initial rate of reaction to determine the order. Okay, so the best thing, if you are given several experiments and you want to find the order of A, B, and C, you have to work one by one. Okay, you have to look at it at one by one. For example, to find the order of A, you look at 2 experiments that only changes A, keeping your B and C constant. Okay, so that's experiment 1 and 2 in this case. So what you have to do is you look at how much the concentration has gone up and how much the rate has gone up. Now, if you didn't know how to do this, like how many times it goes up or how many folds it goes up, you take the bigger number, divide by the smaller number. So in this case, 0.2 divided by 0.1, that's 2. So that means the concentration has gone up by 2. Now, the example that you have in your notes is easy, nice number, but in your exercise you may have seen that it's not as straightforward because it's not a whole number. Okay, likewise for your rate, if you want to know how much your rate has increased from experiment 1 to experiment 2, you take the bigger number, 0.2 divided by 0.1, so that is again an increase, a factor of 2. Okay, for reactant B, you look at experiment 2 and 3. 1 and 3. Okay, because only B is changing between 1 and 3, while skipping your concentration of A constant, concentration of C constant as well. Okay, for reactant C, you use experiment 1 and 4. Okay, if you look at experiment 1 and 4, only the concentration of C is changing. Okay, keeping your A and B constant. Now, the reason for this is you want to know what is the effect of that particular reactant on the rate. Okay, if you start changing to concentration, in which you have done in the homework, I just realized that we haven't gone through the example yet. Okay, if you start changing concentration of 2 reactants at the same time, we see it as a combined effect. Okay, so that brings us to the next one, next example, which is example 2. Okay, example 2 is on page 7 of your notes. So please make sure that you are on page 7 of your notes. Great, we have a full attendance today, well done. Right, so in most questions, it is possible to compare between 2 experiments where only one reactant is changed. Okay, so this is the example 1 that you saw previously, right? If, however, both reactants are changed, then the effect of the changes are multiplied together. So we call this the combined effect. Okay, so let's have a look. First, we deal with reactant X first, okay? So I don't know what reaction this is, but I am going to assume that X and Y are my reactants, right? And then I want to know what is the effect of changing concentration of X on my rate separately, and then what is the effect of changing the concentration of Y on the rate, again, on a separate investigation. Okay, right. So let's see. For X, I think it's the easiest one to start with, right? If you look at experiment 1 and 2, okay, only the concentration of X is changing. That is from 0.1 to 0.05, sorry, from 0.05 to 0.1. And that looks like a multiple of 2, okay? The concentration has increased by 2. No changes to the Y, which is great. So that means we can investigate on X alone, right? Next thing to do is to look at the rate. Now you may be, some of you may be questioning, like, how do we find this multiplication, this factor, or sometimes called fault, okay? As I said, as I mentioned earlier, you take the bigger number. In this case, it's 0.3 times 10 to the power of minus 6, divide by the smaller number. 0.15 times 10 to the power of minus 6. Okay, I hope all of you have your calculator with you so that you, if you cannot see it, okay, you can start calculating. But from 0.15 to 0.30, that is actually a factor of 2 as well, an increase by 2 folds, right? So the concentration increases by 2, the rate increases by 2 as well. So that means the order is first order, okay? Do not get confused. Just because it increases by 2, it is not second order, okay? To determine the order, we look at the effect. Concentration is 2, rate is 2. They are directly proportional, okay? You increase by 2, rate increases by 2. Right? So to write this down, hold on, how do I, okay. For reactant X, compare between experiments 1 and 2. As concentration of X doubles, the rate doubles as well, okay? Therefore, the order with respect to X is first order. Oops. Okay, so please make sure this is the format that you would use in your answer, right? Most of you, well, you managed to answer first order, but you need to have some sort of explanation. Why have you come to a conclusion that it is first order with respect to X? Okay, just look at the change of the concentration and the rate. So please copy this down, and please make sure also that you write down this factor or fault times by 2 times by 2, so you know how you have determined the effect. Okay, right now you may have no problem because it's still fresh, but in months time maybe you will forget, like, how did I get it? Where is this doubling happening? Okay, I'll give you time to copy. Please let me know if you have done copying so that I can move on.
What if the rate, like the concentration doubles, but then the rate,
sorry,
like the concentration doubles, but then the rate, it only increases slightly? Is it still first order?
Increases slightly, what does it mean?
Like instead of 0.15 to 0.3, it goes from 0.15 to 0.2. Like it doesn't double, but it increases.
Yeah, so if that is from the experiment, 0.15 to 0.2, 0.2 is closer to 0.15, right? So that would be zero order. That means it's no, there is no change. Okay, but usually, hopefully in questions they would give you a very significant change, you know, nothing that is vague. Okay, because going from 0.15 to 0.2 is a bit vague, like, is it doubled or is it the same? Okay, yeah, good question, Shakirin. Can I move on now to the next slide?
Yes.
Okay. Right. Next one is we want to look at reactant Y. Now, if you look at reactant Y, experiment 1, 2, and 3, there are no two particular experiments that just change Y, okay? If you look at experiment 1 and 2, Y is not changing at all, so you can't use 1 and 2 because it will not give you any insight on the effect of changing concentration of Y because Y is not even changing. 1 and 3, okay, if you look at 1 and 3, 0.1 to 0.2 of Y, that looks like a double to me. 0.05 to 0.20, that looks like a multiple of 4. You can use experiment 1 and 3 here, okay? But the easiest one is experiment 2 and 3, right? For experiment 2 and 3, the concentration of Y increases from 0.1 to 0.2, so that's doubling. Your concentration of X also increases, which is a double as well, okay? Doubled. So you cannot ignore X. You have to take into account, even though I always said you only change one concentration at a time, but there are some cases where they will change two concentrations or more at the same time, okay, provided that you already know the order of X, okay? If you didn't know the order of X, then that is not possible, right? Okay, let's see, how do we do this, right? So for Y, you go from 0.1 to 0.2, that is a fault of 2. We say it's doubled or it increases by 2. Now, don't forget that your X is also increasing by 2 from 0.1 to 0.2. Okay, you must take these two into account, right? So now the rate. If you can see this immediately from 0.3 to 2.4, that is a multiple of 8. If you cannot see it, then I would ask you to take your calculator. 2.4 times 10 to the power of minus 6, divide by 0.3 times 10 to the power of minus 6, okay? Now this fault of 8 or increase by a factor of 8 is actually a combined effect of changing your X and changing your Y, okay? So it's a combined effect. That means times 8 is caused by your X as well as your Y, okay? Now, thankfully, we already know the order of X, okay? The order of X is first order. First order means whatever increase of concentration, you have the same increase on the rate, okay? Directly proportional. So in this case, you saw that, I've lost my cursor again. There we go, okay. So you saw that the concentration of X increases by 2, therefore the rate must also increase by 2. Okay, so let's see. So this times by 2 is the effect that comes from X, this one, right? Now, if you break this down, minus X, factor of 8 is equals to times 2 times by 4. Do you agree? So this times 2 is actually the effect from X, and this times 4 is actually the effect from Y. Now, we don't have to worry about X. We already know the order. Even though you use different experiment, the order of X will always be the same in that particular reaction, okay? X will always be first order no matter how much you use for the same type of reaction. Now, so we just have to focus on Y. Let's see. Let's have a look at Y, okay? So as you increase the concentration of Y by a factor of 2, the rate increases by a factor of 4. So what does that tell you? 0 first or second? Anyone would like to try?
Second order.
Second order, that's right. Okay, so y is actually second order. Now, please don't think that this factor of 8 is solely caused by y. It's actually a combined effect of x and y. So you have to think about what is the effect on the rate when you double the the x, and then the remaining must be from the effect of changing y. Okay, right, good. So for reactant Y, compare between experiments 2 and 3, the rate goes up by a multiple of 8. Okay, we know that already. We know that X is first order. Since X is doubled, that will double the rate. So that's why we have times 2. When we change the concentration of X, the rate is also multiplied by 2, right? So we're left with this multiplied by 4 in the rate. The effect of y on the rate must be to quadruple it. Okay, as we double the concentration of y, the rate is quadrupled. Or as we increase the concentration of y by 2-fold, the rate increases by 4-fold. Okay, so this tells you that y is second order. So please copy this down. I hope that is clear to you. Is that okay?
Yes.
Your homework, question 1 is actually this, the combined effect. Okay, so if you didn't get it right, please change it on your paper. I've already marked some of your papers. I've marked the ones who have passed it up earlier. I've marked your papers. Link is already given to you. Please go to that link, find your name, find your paper, and then look at the mistakes that you have made. Okay, and correct it yourself on your paper. Okay. How's it going? Okay, can we move on? Okay, right. So I hope that is clear. Don't forget about this combined effect, yeah? The order with respect to y is second order, and then you have to write down the overall rate equation, okay? Rate equation is equals to k times by the concentration of x to the power of 1, so that's just square bracket x, and times by the concentration of y to the power of 2, okay? I hope you managed to get this as your rate equation. The question is asking you to write down the rate equation. There's a box next to, for reactant Y. Please write down the rate equation. Is this okay?
Yes.
Okay, moving on. To calculate the numerical value of a rate constant, so we are going to use this example too to find the rate constant. Okay, so some of you are still, some of you managed to work out the units for rate constant K, but some of you still get confused. Okay, so let's just have a look so that you can do correction for your homework. Okay, now calculating the rate constant K. Using the above reaction, for as long as it is the same reaction, you can choose either experiment 1, experiment 2, or experiment 3 to work out your rate constant K. It will be the same. Okay, the idea is because you're only changing the concentration. Your rate constant will stay the same. The only factor that will change your rate constant is temperature. Okay, in which case you haven't done any temperature change for this equation, for this example too. Okay, right, so please choose one experiment, whichever you want, experiment 1, 2, and 3. But if you choose one experiment, please make sure you only use the concentration of experiment 1. Do not mix them up. Okay, take the concentration of experiment 1 for X, take the concentration of experiment 1 for Y, take the rate for experiment 1, right? If you want to choose experiment 2, that is fine. You will use 0.10 for your concentration of X, you will use 0.10 for the concentration of Y, and your rate will be 0.30 times 10 to the power of minus 6. Okay, so please, you would need a calculator for this one. Please calculate it using a calculator. Do not try to use your head because it doesn't work. There's a factor of 10 to the power of minus 6.
Miss,
Yes?
can you repeat from the overall rate equation? Just now, the audio is not good.
Okay, overall rate equation, this one. This one? Is it this one, Fatim? Rate is equals to K times the concentration of X times the concentration of Y squared. So
Yes.
if you want to find K, the rate constant, so you really have to read the question. Is the question asking for the rate or the rate constant? Okay, rate constant K, you have to rearrange. Okay, this is for the next part, yeah, which is the bottom part. So if you want to calculate K, you need to move these terms to the other side. Okay, so rate, just choose one experiment. If you want to use experiment 1, that's the easiest. Rate is 0.15 times 10 to the power of minus 6 over concentration of X, which is 0.05, concentration of Y, 0.1. Don't forget to square it. Okay, you need to square it. You need to follow your rate equation. Okay, the answer for your K rate constant should be, do I have the answer here? No, the answer should be 3.0 times 10 to the power of minus 4. Did you get that? 3 times 10 to the power of 3.0 times 10 to the power of minus 4.
Yes.
Yes, okay, as for the units now, this is where I'm going to teach you how to work out the units of K. Same thing, you take your rate equation, you rearrange it, bring these terms, these concentration terms to the other side so that you get that. Oh, sorry. Okay, now your rate is always change in concentration over time. So the units of rate is always mole per dm cube per second. That is all. Okay, it will always be that regardless of whatever your order is, your units of rate is the same. So this brings back to the very first thing that we looked at in this topic. Okay, you can always go back to page 1 of your notes. So the units of rate, I lost my cursor again, is mole per dm cube per second. And then the units of the concentration term is mole per dm cube times by mole per dm cube square. Okay, you cancel whatever can be canceled. So it looks like the top and bottom mole per dm cube can be cancelled. Okay, so you're left with mole square dm minus 6 at the bottom. And of course, you carry this up. It becomes mole minus 2 dm now becomes positive 6 and second to the power of minus 1. Is this okay for you?
Yes.
Okay, so you cannot memorize the units of K. I won't suggest you to memorize it. It's better that if you work it out. But what you need to memorize is the units of rate. It will always be mole per dm cube per second. Okay. Right, so your answer is this: 3 times 10 to the power of negative 4 mole per, mole to the power of minus 2. Oh, what is wrong? dm to the power of 6 second to the power of minus 1. Okay, if you don't have a calculator with you, please just write down the final answer and then you can work it out later. Is that okay?
Yes.
Can we
Yes.
move on?
Yeah.
Okay, so for example 3 and 4, I've marked some of yours who for those who handed in early, I've marked them. But if you haven't received your feedback, please just mark it now. The time is 7,200 seconds. Okay. For question 2, it is asking you for the rate constant. So K. The unit for a rate constant for a first order reaction is second to the power of minus 1. Okay, even from this expression, you can see that times T half is in second, ln2, no unit, K would be S minus 1. Okay, how do you work out K? You just bring K to the other side and then the second goes down and you will get S minus 1. Okay, next. I've lost my cursor again. I have 10 minutes left. What time is it? Okay, just nice. Right, moving on. Explain qualitatively the effect of temperature change on the rate constant and hence the rate of reaction. So this is something that you know already. Only by changing the temperature will your rate constant change. Okay, increasing temperature increases the value of the rate constant K, hence the rate of reaction increases. Changing the concentration will not affect the rate constant K. So this is evident from example 2, where experiment 1, 2, 3, you are changing the concentration of the reactants, yet your rate constant is the same for all 3 experiments. Okay, so rate constant in a way is the same as your equilibrium constant, where it is only affected by the change in temperature. Okay. This is something that you have learned already. An increase of 10 degrees Celsius approximately doubles the rate of reaction, but we will not go into further details for that, right? The next one, I will just talk about it briefly since we have 8 minutes left. The next one, we're going to look at the mechanism of a reaction, okay? Actually, your mechanism, if you still remember, is this steps, the processes that shows the movement of electrons. So your bonds are broken, your electrons are moving. some species accepts electrons, some species donates electrons, and etc. So this is what we call mechanism. Okay, so mechanism is actually related to your rate equation. So on Monday, I'll explain to you how. Okay, basically, this one, if looking at example 1, which you don't have in your notes, but that's fine. Okay, so example 1, you have the equation. This is the full equation. The equation only tells you the reactants and the products. Okay, that's that is all that it can tell you. But the mechanism shows you the transformation, the stage, how your reactant turns into your product. Okay, so a reaction, even though we see it as one line, like straightforward from reactants to products, sometimes they involve a multi-step stages, okay, or multi-stages. That means to transform my reactants to products, I need 2 steps for this reaction, okay, for this particular reaction. This is a reaction that you have seen already in AS. This is your SN1 nucleophilic substitution. Okay, it's halogenoalkane, your organic chemistry. Okay, so let's just look at the definition first. A mechanism is a series of steps through which the reaction progresses, often forming intermediate compounds. Okay, so these 2 steps are mechanisms. This is your equation. Okay, your mechanism shows that in order to transform your reactants to products, it requires 2 steps or 2 stages. And in the process, you form an intermediate. Now, this is your intermediate. We call this the carbocation. If you notice, the carbocation or your intermediate does not show in your equation. Okay, so equation is really the summarized version. Okay, you don't see what's happening. You don't even know that there is an intermediate unless you learn the mechanism. Okay, so adding all the steps will add up to, when the steps are add up together, the overall equation for the reaction will be given. Okay, so when you add step 1 here and step 2, overall it will be the same as your equation. Okay, what happens? Because your intermediate will be cancelled out, or your intermediate will be used up, so you don't see intermediate in the equation. Okay, so each step can have a different rate of reaction. So this is step 1, step 2. They do not have the same rate. In this case, step 1 is the slowest step for this reaction. Step 2 is the fastest rate. How do we know which one is the slowest, which one is the fastest one? Now, this is where your rate equation comes in. Okay, the slow step in a reaction, even if you have like 5 stages or 5 steps, one of them will be a slow step. Okay, and that slow step is what we call the rate determining step. Okay, that means out of all the steps in a particular reaction or in a particular mechanism, only this step, the slow step, will determine the rate. Okay, so there is a connection between this slow step and your rate equation, which I will talk about on Monday. Right now, sometimes the slow step can be the first step, sometimes it can be the second step, sometimes it can be the third or the last step. So there is no definite pattern. Okay, how do you know that? We can only know it from the rate equation, right? So the new term, which is frankly not new because you have come across this term in AS, whenever you see a slow step in a mechanism, we call this the rate determining step. So you need to know, you need to be familiar with that term. Okay, RDS. If you look at the mechanism that I draw for you in your AS organic topics, I have written it down as RDS, rate determining step. So the moment you see RDS, you know that that step is the slowest, and then the rest is the fastest. Okay. Right, so that is all. Let me just stop